Here I would like to talk about bond rotation and geometric isomers. I'm going to focus on the difference between a carbon-carbon single bond and a carbon-carbon double bond and how that can lead to the formation of geometric isomers. We want to consider ethane, which is a gas at room temperature. It's a hydrocarbon. It has a condensed structural formula shown here of two methyl groups bonded to each other. The methyl groups are bonded through a carbon-carbon sigma bond. That's a single bond. So you think of each carbon being sp3 hybridized. This one on the left here has an sp3 hybrid orbital pointing to the right. This one on the right has one that's pointing to the left. And those two sp3 hybrid orbitals will overlap and they will form what is called a sigma bond. What's interesting about ethane is that these methyl groups actually act like rigid rotors and they freely rotate relative to each other. This is illustrated in this stick model, three-dimensional stick model of ethane. As you see here, we have two carbons, two methyl groups, and this particular model here shows what is called an eclipse conformation. That is, this hydrogen right here eclipses this hydrogen right behind it. And the same is true for these other pairs of hydrogens. So we have an eclipse conformation of ethane. But it turns out that the methyl groups can rotate freely relative to each other. So we can take this methyl group in the front and rotate it. It essentially whirls around like a top relative to the other one. You can arrive at another conformation called a staggered conformation. In this conformation, this hydrogen here in front that I'm indicating here is exactly between these two hydrogens that are in the back. So there's both an eclipse and a staggered conformation, but it can go back and forth. It can freely rotate. In fact, rotation is thought to be very fast. It's been calculated recently to rotate 120 degrees in a time period of 12 picoseconds. That's 10 to the minus 12 seconds. So that's a very rapid rotation. So at room temperature, ethane is undergoing rapid single bond rotation. We can contrast that with the rotation about a carbon-carbon double bond of ethene. Ethene has the double bond, and therefore it has that ENE ending. And it turns out that rotation of that double bond is very slow and essentially non-existent at room temperature. Now, if you look at ethene, you see the double bond between the two carbons. The carbons are both sp2 hybridized, and the double bond consists of one sigma and one pi bond. We can take a look at a model down here of ethene. Sometimes this is called ethylene, but it's a gas just like ethane. And you can see that there's a carbon-carbon sigma bond here, and that's formed from the overlap of sp2 hybrid orbitals. And then there's also a pi bond, which is formed by the overlap of parallel p orbitals on the sp2 hybrids. So there's an overlap both above the sigma bond and below the sigma bond to constitute one pi bond. So we have one sigma bond and one pi bond. Now, if we think about how that might rotate, one could actually do that, but what's going to happen if you do rotate it is you're going to have to break the pi bond in order to do so. The sigma bond would remain intact, but the pi bond would have to break because these two p orbitals that form the pi bond would have to move relative to each other, and that would destroy the overlap of the two parallel p orbitals. So these would be perpendicular to each other, and I would have to break the bond. So the overlap would be destroyed. So it turns out that that's energetically unfavorable. That's a very difficult thing to do, and therefore the double bond is a rigid bond, and there will not be free rotation at room temperature. Well, it turns out that because of the lack of free rotation of the carbon-carbon double bond, it leads to something called geometric isomers. But before I talk about geometric isomers, I just want to talk about isomers in general and classify some different kinds of isomers that we're going to encounter in organic chemistry. The first one is called what is called a constitutional isomer, and sometimes called a structural isomers. And these are isomers that differ in their bonding sequence. That is, their atoms are differently connected. So for example, here's a molecule, which is a hydrocarbon, which has 5 carbons, called pentane. This is called normal pentane. That's what the N stands for. But you'll notice that all the carbons are in a line here. They're all straight chain hydrocarbon here, so to speak. They're all in this row right here. That's normal pentane. You also notice that isopentane is here. That's also got 5 carbons, but you'll notice what it is. It's a branched hydrocarbon. That the binding sequence of these carbons is different in isopentane compared to normal pentane. Well, these would be called constitutional or structural isomers of each other. They all have the same formula, but they're bonded differently. They have a different sequence of bonding. Here's neopentane. You'll notice it has 2 branch points. So it has 3 carbons and then a methyl off the side, another methyl off the side. So all 3 of these are constitutional isomers. There's another kind of isomer that we'll encounter later on in a later chapter, and these are called stereoisomers. Stereoisomers are isomers that differ only in how their atoms are oriented in space. In fact, their connectivity or their sequence of bonding is exactly the same, but they have a different spatial orientation. One example of stereoisomers are these 2 molecules here. These are alkenes. They have 4 carbons, but you'll notice that there's a carbon-carbon double bond in each one of these. This one here, where the 2 methyls are on the same side of that double bond, is called a cis isomer. So that's the cis isomer, the 2 methyls being on the same side. This isomer over here shows that the 2 methyls are trans to each other with respect to the double bond, that meaning that they are on opposite sides of the double bond, not on the same side of the double bond. So we have cis and trans. The important point here is that these are actually not interconvertible at room temperature. They're rigid because of the double bond. We don't have free bond rotation about that carbon-carbon double bond. Therefore, you have the cis isomer, and that exists separately from the trans isomer. Only if you heat it to really, really high temperatures would these interconvert. But at room temperatures, they're going to exist as separate isomers. So these are called cis-trans isomers, and they're sometimes called geometric isomers. And that's because they have a different relative position with respect to that double bond. So we have the cis and the trans. These have different properties. They can be separated from each other in principle, and they have actually geometric isomers in this case.